Welcome to The Explainer. Today we're going to dive into the long and honestly fascinating history behind all those AI images you see everywhere. You know, the photorealistic faces, the impossible landscapes. Yeah, that didn't just happen overnight. It's actually the result of a scientific quest that's been going on for decades.
Okay, so let's get right into it because long before you ever heard of DALL-E or Midjourney, there was this single unifying goal that was driving researchers for decades. It was a kind of holy grail for the entire field of image processing.
And that goal, that holy grail, well, it can be summed up in just three little characters. Now, it might not look like much, but trust me, understanding this is the key to pretty much everything that followed.
This is it, P of X. Now, I want you to think of this as a universal map of all possible images. It's a function so powerful that it knows the exact probability that any random mess of pixels actually forms a coherent picture. You know, like a cat or a sunset or your best friend's face. If we had this function, my gosh, we could do anything. We could generate any image imaginable, and we could also perfect tasks like removing noise from a photo or sharpening a blurry picture. It's the whole shebang. So, for nearly 5 decades, we're talking from the 1970s all the way to the early 2010s, the whole quest was about trying to write down the formula for PX by hand. Yeah, researchers were literally making these super educated guesses about the fundamental properties of images. And you know, the thinking really evolved over time. Back in the 70s, the big idea was that natural images are generally smooth, right? So the models were built to favor that smoothness. Then, in the 80s, the field got a bit more statistical, assuming that image data followed a Gaussian, or a bell curve distribution. And by the time we hit the 90s and 2000s, the dominant idea was something called sparsity, that you could represent images really efficiently with just a few key components, using cool tools like wavelets. But here's the kicker. Despite all of this brilliant work and decades of progress, all of these classical models, they all shared the exact same fundamental flaw. They just couldn't do it. They couldn't synthesize or hallucinate a convincing new picture. It's like they had all these sophisticated rules describing what an image should look like, but they had no way to use those rules to just generate one out of thin air. It was this huge, gaping hole in the puzzle.
And then, around 2014, something happened. A massive conceptual shift that changed the entire quest forever. And that thing was, of course, the rise of deep learning. It offered a completely new way to attack the problem. So this is the crucial point, right? The field basically stopped trying to write the perfect map of all images. Instead, they said, you know what? Let's just focus on building a machine that can go visit the land of images and bring us back some souvenirs. So instead of describing the rules, they decided to learn by example, by training these massive neural networks on millions and millions of real pictures. And this pivot, this huge shift from describing to sampling, well, it led to what you can only call a Cambrian explosion of different approaches. Suddenly, it felt like everyone was building their own version of an AI artist, and each one had a totally unique way of learning how to create new images. Okay, so first up to the plate were variational autoencoders, or VAEs for short. And the easiest way to think about a VAE is as a really, really clever compressor and decompressor for images. So here's how the magic works. An encoder network takes a real image and it just squishes it down into this tiny, compact representation, its essential essence. We call that a latent code. Then, a decoder network has to learn how to take that tiny code and rebuild the original image perfectly. Once that decoder gets really good at its job, you can just throw the encoder away, give the decoder new random codes, and it'll generate brand new images that follow all the patterns it learned. Pretty cool, right? And this really gets to the core trade-off with VAEs. On the one hand, they are amazing at organizing concepts. You can literally do math with these codes. You can find the code for man with glasses, subtract the code for man, add the code for woman, and bam, you get an image of a woman with glasses. But on the flip side, that pressure to be able to reconstruct images perfectly often forces them to average things out, which leads to kind of blurry, fuzzy results. So next on the scene were GANs, or Generative Adversarial Networks, and this was a totally different philosophy. This approach is based on a rivalry, a competition between two AIs that are constantly trying to one-up each other. It's this incredible constant cat-and-mouse game. You have one AI, the generator, and its only job is to be a forger, to create fake images. Then you have a second AI, the discriminator, which acts like an art detective. It trains on tons of real images, so it gets really good at spotting the forgeries.
And as they compete, the forger gets better by fooling the detective, and the detective gets better by catching the forger. They just keep pushing each other to improve over and over again.
And that adversarial process is exactly why GANs can produce these unbelievably sharp and detailed images. I mean, the kind you see on websites like This Person Does Not Exist. But that two-player game, that's also their biggest weakness. It can be incredibly unstable and a real headache to train, kind of like trying to get two rivals to cooperate perfectly. It doesn't always work out.
So, this explosion of new models leads to a really important question. If you can't just trust your eyes to spot subtle problems, like, say, an AI that only generates golden retrievers, even though it was trained on all dog breeds, how do you objectively score an AI artist? How do you know who's winning? Well, this need for a fair comparison led researchers to develop a kind of official scorecard, a way to actually measure and compare the performance of all of these different generative models. And they came up with several metrics. The most famous one is probably FID, or Frechette Inception Distance. It basically just measures if the statistical vibe of the generated images matches the vibe of the real ones. For that one, a lower score is better. And then you've got precision and recall. Precision asks, okay, of all the images you made, what percentage are actually good? While recall asks, how much of the diversity of the real world did you manage to capture in your fakes? So when you think about this entire quest, from people making educated guesses about image smoothness to this huge pivot towards deep learning that created a whole zoo of competing AI artists like VAEs and GANs, it was all building towards the next great breakthrough. And that breakthrough, the current champion in this long quest for PX, is a class of models you've probably heard a ton about recently, diffusion models. They are the powerhouse technology behind so many of today's most incredible image generators. Which leaves us with a final kind of provocative thought. After all these decades of trying to define images, compress them, or forge them, what if the secret to creating any picture imaginable wasn't about any of that? What if it was about something much simpler? Just learning how to meticulously clean up static. Well, that's the core idea behind diffusion, and it's the next chapter in this incredible 70-year story.